video, I'm going to teach you the basics of electric charge, and let's get started. What is an electric charge? Okay, in order, before going into the details of what an electric charge is, let's take some real life examples which gives us an overview of what an electric charge is. In your dry weather, you can produce a spark by walking across certain types of carpet and then bringing one of your fingers near a metal doorknob. You can also produce multiple sparks when you pull a sweater from your body or clothes from a dryer. Sparks and the static cling of clothing are usually just annoying. However, if you happen to pull off a sweater and then spark to a computer, the results are more than just annoying. These examples reveal that we have electric charge in our bodies, sweaters, carpets, doorknobs, faucets, and computers, whatever. In fact, every object contains a vast amount of electric charge. And for our question in the starting of a video, what is an electric charge? Electric charge is an intrinsic property of the fundamental particles making up those objects. That is, it is a property that comes automatically with those particles wherever they exist. As I said before, electric charge is an intrinsic property of the fundamental particles making up those objects. And one of the most important point is charges with same sign repel each other and charges with opposite sign attract each other. The vast amount of charge in everyday object is usually hidden because objects contain equal amounts of the two kinds of charge, positive charge and negative charge. With such an equality or balance of the charge, the object is said to be electrically neutral. That is, it contains no net charge. If the two types of charge are not in balance, then there is a net charge. We say that an object is charged to indicate that it has a charge imbalance or net charge. The imbalance is always much smaller than the total amount of positive charge and negative charge contained in the body. Charged objects interact by exerting forces on each other. Let us take an example of Coulomb comb and paper example. When we rub a comb against our hair and place it near pieces of paper, the paper would fly towards the comb. This is due to the electric charges present on these bodies and the force acting on these bodies. This is one of the most basic or most easiest example you can do at your home to find out the forces on electric charges. One of the most common example is the silk rod and the silk cloth and the glass rod example. When you rub a glass rod against a silk cloth and hang one of the glass rod from the wall, and when you bring another glass rod towards the hanging glass rod, the, the hanging glass rod fly apart. That is due to the same charge acquired by the two rods. As we said earlier, like charges repel, unlike charges attract. The positive and negative labels and signs for electric charge were chosen arbitrarily by Benjamin Franklin. You can also name as your way, but the convention is that given positive and negative labels for electric charge. Benjamin Franklin was followed by everyone in the world. The attraction and repulsion between charged bodies have many industrial applications, including electrostatic paint spraying and powder coating flash collection in chimneys, non-impacting jet printing and photocopying, etc. The figure here shows a carrier bead in a photocopying machine covered with particles of black powder called toner. These are the toner particles, and the inside one is carrier bead. The negatively charged toner particles are eventually attracted from the carrier bead to a rotating drum where a positively charged image of the document being copied has formed. A charged sheet of paper then attracts the toner particles from the drum to itself, after which they are heat fused permanently in place to produce the copy. Okay, we can classify materials generally according to the ability of charge to move through them. Conductors are materials through which charge can move rather freely. Examples include metals, the human body, and tap water, etc. Non conductors, also called insulators, are materials through which charge cannot move freely. Examples include rubber, etc., and so on. Semiconductors are materials that are intermediate between conductors and insulators. Examples include silicon and germanium, which are used in computer chips, most famous in nowadays electronic equipment. And one of the other classification I have not mentioned here is superconductors. These are the materials that are perfect conductors, allowing charge to move them without any hindrance. Almost resistance equals to zero. In these examples, we have discussed only conductors and insulators. That's all about the materials classification based on the charge movement through them. And next is the Coulomb's law. Coulomb's law is one of the most fundamental law related with the forces on charged bodies. And in order to explain Coulomb's law, we get some of the information relating that to that law. Okay, let's start. If two charged particles are brought near each other, they each exert a force on each other. If the particles have the same sign of charge, they repel each other, as I said earlier. And that is the force on each particle is directed away from the other particle. And if the particles can move, they move away from each other. If instead the particles have opposite sign of charge, they attract each other. And if free to move, they move closer to each other. This force of repulsion or attraction due to the charged properties of the objects is called electrostatic force. The force of attraction or repulsion due to the charged properties of the objects is called electrostatic force. The equation giving the force of charged particles is called Coulomb's law. It was named after the Charles Augustin de Coulomb, whose experiments in 1785 led him to it. And the Coulomb's law equation was given as F is equals to K into Q1 Q2 by R square R cap, where K is a constant and Q1 Q2 are the magnitude of charges placed here, where r is the distance between them. And this equation here seems to be an analogy with the gravitational force between two bodies. K is called electrostatic constant, and its value is equals to K equals to 1 by 4 pi epsilon naught, and numerically it was equals to 8.99 into 10 to the power 9 Newton meter square per coulomb square. 10 meter square per coulomb square. And here the epsilon naught is called the permittivity constant, sometimes appears separately in equations, and its value is equals to 8.85 into 10 to the power minus 12 Newton meter square. And there are two properties attached with the charges, until now we have discussed it about. One thing is that charge is quantized. What do you mean by quantization is that when a physical quantity comes in discrete values, it is said to be quantized. And we believe that charge is equal to the charge on a body, the charge acquired by a body is equals to integral multiples of electron, the charge on the electron. Here Q is equal to Ne, where N can be plus or minus 1, plus or minus 2, and plus or minus 3, and so on. And when we see here, N can acquire only integer values, that is, the charge on a body can be 2 times of charge on the electron, or 3 times of charge on the electron, or the charge of the electron, and that's the way it goes. And we have the charge on electron E is equals to 1.602 into 10 to the power minus 19 coulombs. And coulombs, and another property of the charge is conserved. The charge is conserved. The conservation of charge is in the same lines of conservation of mass. As mass can neither be created nor be destroyed, in the same way charge can neither be created nor be destroyed, but it can be transferred from one body to the other. When we take an example of let's take an example of electron and a positron. Positron is an antiparticle which has the same magnitude of charge but opposite that of electron. When you take an example of these two annihilation processes, that is, when we annihilate the positron and the electron, they gives rise to two gamma particles and how can this apply to our conservation principle is in the following way. In order to apply our conservation principle, we should follow the conservation principle as follows. the total charge before the reaction occurs and the total charge after the reaction occurs. When we add the two charges, and the net charge will be 0 before the reaction, and here both the gamma particles have no charge, that is they are neutral. So after the reaction the total charge is 0 and therefore the charge is conserved. Another important example related to the charge conservation is the radioactive decay of nuclei, in which a nucleus transforms into a different type of nucleus. For example, uranium 238 nucleus transforms into a thorium 234 nucleus by emitting an alpha particle. Because the particle has the same makeup as the helium-4 nucleus, it has the symbol for helium. The number used in the same of a nucleus as a superscript in the symbol for the nucleus is called as mass number and is the total number of protons and neutrons in the nucleus. For example, the total number in uranium 238 is 238. The number of protons in the nucleus is the atomic number Z, which is listed for all elements in the periodic table. The parent nucleus uranium 238 has 92 protons and thorium 234 has 90 protons. And after the reaction we got a helium, that is alpha particle, contains 2 protons and we see that the total charge is 92 before and after the decay. Thus the charge is conserved, which is also the best example for conservation of charge. And that's all for the introduction of the charge, and thank you for watching my video, and please like and subscribe my video for more videos about the electrodynamics, and I will be going to upload more videos in the upcoming days. Thank you for watching my video.